Morning students, in class 12 physics unit 7 dual nature of matter and radiation. Our today's topic is dualistic, de Broglie dualistic hypothesis. Okay, as we learned in the previous class, radiation have dual nature. It will proved by the photoelectric effect and some more effects like Compton effect and X-ray experiment, which proved that the radiation have the particle nature also. Hence, according to those experiments, we conclude that radiation behave as matter or sometime as radiation, which proved its dual nature. Okay, now next we have to study about how the matter is behave like radiation. Okay, for doing so, uh, de Broglie do some work to explain it ki how the matter is behave like a radiation. Okay, according to him, the matter sometime behave like radiation and sometime behave like wave matter, and according to him, the wave associated with the material particle is controls it in all respect. So according to the de Broglie hypothesis, according to de Broglie uh, a moving material particle sometimes acts as a particle and sometimes as a wave. Okay, or a wave is associated with moving moving material particle which controls the particle in every respect. Okay, the wave associated with moving material particle is called the matter wave. The matter wave or de Broglie waves. De Broglie wave. Okay, and wavelength of wavelengths of these wave is called de Broglie wavelength. De Broglie wavelength. Wavelength. And it is given by lambda is equal to h upon mv, where lambda is de Broglie wavelength, h Planck's constant with value 6.63 into 10 to the power minus 34 joule second. Okay, and m is mass of particle, and v is velocity of particle. Okay, now derivation for de Broglie wavelength. Okay, now according to Planck constant, according to Planck's quantum theory, the energy associated with photon, or say material particle, is given by E is equal to h nu. Okay, and we know that nu is equal to c upon lambda. Therefore, energy associated with it is hc upon lambda. Now, from here we get lambda is equal to hc upon E. This is equation first. Okay, now according to Einstein mass energy relation, mass energy relation, energy is given by mc square, where m is mass of particle and c speed of light, speed of light. Okay, by putting this value in equation first, we get lambda is equal to hc upon mc square, as we have value lambda is equal to hc upon e. Okay, therefore we get lambda cancel this square of denominator and this will become mc. Okay, h upon mc, where mc is momentum of particle. Okay, therefore lambda is h upon p. Okay, now if a particle, or we say for electron, proton, neutron, neutrons, etc. Okay, accelerated particle having mass me, mp, mn and velocity v. Therefore momentum is given by m into v. Therefore from equation A we can see that lambda of the particle is h upon mv. This is the required derivation for this is required relation for de Broglie wavelength. Okay, now this would be lambda is h upon p, which is equal to h upon mv. Okay, now for de Broglie wavelength from equation A, that is lambda is equal to h upon mv. Here the wavelength is a function of velocity, wavelength is a function of mass. Okay, this is case 1 and this is case 2. For first case we have two situations. 1a, when velocity is equal to 0, we get the wavelength of the de Broglie wave is infinite, because lambda is equal to 1 upon 0. Okay, so in this case there should be a uncertainty to find the position of the particle of the de Broglie wave. or de Broglie matter moving particle. Okay, and if lambda becomes 0, therefore velocity of particle become infinite, as velocity is inversely proportional to lambda. Again the same situation, if the velocity of the particle is infinite, then it is moving with a very fast speed and it is very difficult to find the location of the particle. Okay, second is B. When velocity is small and large, we get lambda is larger, and for the second case lambda is small or smaller. Okay, now case second, that is lambda is inversely proportional to the mass of the particle, which indicates that wavelength associated with de Broglie wave is small for heavier particle. For heavier particle. Okay, and vice versa. Next, okay, next we have the de Broglie wavelength of an electron. Okay, so consider an electron of mass m and charge e. Let v be the velocity acquired by electron when accelerated from rest through a potential difference of V volt. Okay, therefore velocity of 1 minute, therefore acquired kinetic energy by electron is given by half mv square, that is k is equal to half mv square. Okay, now work done work done on electron to give energy to get the velocity mv square, okay, is equal to ev. Therefore this is equation first and this is second. From equation first and second we get ev equal to half mv square, that is kinetic energy is equal to work done, okay. Therefore from here we calculate value of v square is 2e v upon m. Therefore the velocity of the particle is under root of 2 ev upon m. Now if lambda is the de Broglie wavelength associated with the electron, then therefore lambda is given by h upon mv, as we discussed. By putting the value of m here we get h upon m under root of 2 ev upon m. This m cancel this root 2m time, therefore lambda is equal to h upon 2 mev. This is the energy of electron associated wavelength or de Broglie wavelength associated with the moving electron. Now by substituting values of each constant in equation A we get lambda is equal to value of h is 6.64 into 10 to the power minus 34 upon under root of 2 into mass of electron 9.1 into 10 to the power 31 into 1.6 into 10 to the power minus 19 into v. This we get after solving. The value of the de Broglie wavelength is equal to 12.27 upon square root v angstrom. That is, the de Broglie wavelength is given by 12.27 under root of v angstrom. This is the value of de Broglie wavelength associated with the electron, okay. Next we have relation for de Broglie wavelength and temperature. Okay. as we have the according to kinetic theory of matter, the average kinetic energy of particle is a given temperature T Kelvin is given by kinetic energy is equal to 3 by 2 kT, where K is Boltzmann constant. Okay, now the kinetic energy of particle of mass m is half mv square. This is equation first and this is second. From equation first and second, from first and second we get kinetic energy. Okay, 3 by 2 kT equal to half mv square. This 2 cancel by this and we get from here v square is equal to 3 kT upon m. Therefore v is equal to under root 3 kT upon m. Okay, now from de Broglie wavelength, lambda is equal to h upon mv. By putting this value we get h upon m 3 kT upon m, that is lambda is equal to h square root 3 m square kT upon m. This m cancel. Okay, so we get the result is h upon p, and this result will become h square root of 3m kT. This is the relation between the temperature, which gives that the wavelength of de Broglie is inversely proportional to the temperature. Okay, this is the relation between the de Broglie wavelength and the temperature, and how we calculate this relation. Okay, so students, this is the topic which is complete of unit 7, and the next part, that is the Davison-Germer experiment, is deleted for this session 2020-21, and here representation of de Broglie wavelength. Okay, it is represented as like this. Okay, here is a particle. This is the wavelength lambda. Let's say here I will just form again. This here is a particle. This is the wavelength lambda. Okay, this is how we represent the de Broglie wavelength. These are de Broglie wave or matter waves. Okay, thank you.